Hi, in this video I was going to show you how to use the website that I want you to use this week. Before I show you how to use the website, I wanted to go through examples to help explain the margin of error and confidence intervals because it'll be good to understand these ideas before you use the website. So right here we have the formula for the margin of error. I wanted to start off by explaining what these symbols stand for. This letter Z right here is called the confidence coefficient. It's looked up in a table, and I'll show you what table you have to go to look it up. This symbol right here is the Greek letter sigma, and it stands for the population standard deviation. The standard deviation of all members of a population. So I said pop SD, which just means population standard deviation. It was just a short way of writing it. And this letter N is sample size. So the formula for the margin of error is the confidence coefficient times the population standard deviation over the square root of the sample size. This symbol right here is just a multiplication sign. So confidence coefficient times population standard deviation over the square root of the sample size. Let's pretend that I'm actually going to take a sample from a population randomly and calculate the mean of the sample to estimate the mean of the population. So I'm doing a study in which I'm going to calculate the mean of a random sample to estimate the mean of a population. Let's say that maybe I'm interested in what the mean number of siblings equals in the JFK student population. I'm interested in what the average number of siblings is across the JFK population. And I can't calculate the population mean because in order to do that, I would have to actually ask every JFK student how many siblings that they have and then calculate the mean of all of that data. I don't have time to survey all JFK students, so I have to settle for selecting a random sample of JFK students and asking the people in my sample how many siblings they have, and then calculating the mean of my sample as a way to estimate the mean of the population. So maybe I decide to select a sample of, let's say, 64 JFK students. I'm going to randomly select 64 JFK students. I'm going to ask them how many siblings they have, and then I'm going to calculate the mean of the 64 people in my sample. I'm going to do that by adding their 64 answers and dividing the total by 64. And then once I get the sample mean, I'll use that as an estimate of the mean number of siblings for all JFK students. And before I actually select my sample of 64 people, before I actually collect data, I want to know what the 95% margin of error equals. And what I'm going to do with you right now is I'm going to go through an example of actually calculating the 95% margin of error. So in order for us to calculate the 95% margin of error, we have to know what my sample size is. And I just said that I'm using a sample of 64 people. So I already know what sample size I'm planning to use. That's going to go right here in the formula. I also have to know what the population standard deviation is. I have to know what the standard deviation of the JFK population equals. Let's imagine that the population standard deviation is 3.2. So somehow I know that the standard deviation of the JFK population is 3.2 siblings. and that's going to go right here in the formula. So I have this, and I have this. All I need is the confidence coefficient, and I told you that that comes from a table. So if you go to Google and you type in small table of z-values for confidence intervals, I'll show you right here. Type in small table of z-values for confidence intervals into Google, and it'll give you the table of confidence coefficients. And I have to decide what margin of error I want to calculate. I have to decide if I want the 90% margin of error, or if I want the 92 or the 95% margin of error. These are all of my choices. And I said that I want the 95% margin of error, which is right here. If I want to calculate the 95% margin of error, then this is my confidence coefficient, 1.96. So I take 1.96 and I plug it into my formula right here for this, where this symbol is. So my confidence coefficient is 1.96. I multiply that by the population standard deviation, 3.2, over the square root of the sample size that I'm planning to use, which is 64. And once we go through all this work right here, we'll have the 95% margin of error. So this is really only going to take 3 steps. And I'll show you what those 3 steps are. First, we have to find the square root of our sample size. We have to find the square root of 64. We can do that by just going to a calculator, entering in 64, and then pressing the square root key. And we find out that the square root of 64 is 8. So right here, we're going to change this to 8. So we found out that the square root of 64 is 8. That's why I took off this and I just replaced it with the 8 right here. The reason why the square root of 64 is 8 is because the square root of a number is just the number that, when multiplied by itself, gives you that number. So the reason why the square root of 64 is 8 is because 8 times itself equals 64. 8 times 8 is 64. So the square root of a number is just the number that, when multiplied by itself, gives you that number. So we finished step 1. We found the square root of 64. It came out to 8. Now step 2 will be dividing this fraction, dividing 3.2 by 8. 3.2 divided by 8 is 0.4. So we're going to change this whole thing to 0.4. Now it's just 1.96 times 0.4. So step 1 was the square root. Step 2 was dividing the fraction. Step 3 is just going to be multiplying. We're going to multiply 1.96 by 0.4 to get our final answer. .96 times 0.4 is 0.78 if we round it to 2 places. So that's our 95% margin of error. It's 0.78. Now we have to wonder, what is this actually telling us? Well, what it's telling me is that when I randomly select my sample of 64 people from the population, and I calculate the mean of my sample, 95% of the possible samples will fall between these 2 points that I'll draw on here. Here's the unknown population mean that I'm estimating. It's the mean number of siblings of all JFK students. And we're going to imagine that this point down here, this dotted line, is 0.78 below the population mean, and this dotted line is 0.78 above the population mean. And this number is just the 95% margin of error. What this 95% margin of error of 0.78 is telling us is that when I randomly select my sample of 64 people and I calculate the mean of my sample, 95% of the possible samples that I could select will have a sample mean somewhere in this area right here, between this boundary point and this boundary point right here. So when I randomly select my sample of 64 people and I calculate the mean of my sample, 95% of the possible samples that I might end up selecting will have a sample mean somewhere between 0.78 below the population mean and 0.78 above the population mean. So the 95% margin of error is just the distance from the unknown population mean that I'm estimating to the lower end and the upper end of the middle 95% of the possible samples. Now, if 95% of the possible samples have a sample mean in this area, then that must mean that 5% of the possible samples have a sample mean outside of this area in the two tails. Because 95 plus 5 is 100, and it turns out that half of that 5% will be in here, and half of that 5% is here, because the two sides of the curve are the mirror image of each other. They're symmetrical. So this has to be half of the 5% right here, and the other half of the 5% out here. So let's actually Let's find out what half of 5% is. 5 divided by 2 is 2.5. That means that 2.5% of the possible samples that I could select have a sample mean down here, more than 0.78 below the population mean. And 2.5% of the possible samples have a sample mean way out here, more than 0.78 above the population mean. So basically, 2.5% of the possible samples have a sample mean more than down here, more than 0.78 below the population mean. 95% of the possible samples have a sample mean within 0.78 of the population mean in here, and the other 2.5% of the possible samples have a sample mean that's more than 0.78 above the population mean, way out here. And these three areas make up all of the possible samples because these three percentages all add up to 100. Now, I haven't actually selected my sample yet. Remember, I've calculated the margin of error, but I haven't actually done my study yet. So there's no way for me to know for sure which of these three areas my sample will come from. And I'm hoping that my sample comes from the middle 95% and not one of the tails, because these are where the most accurate samples are. And we can actually figure out what the probability is of me getting a sample in this area, what the probability is of me getting a sample in this area, and what the probability is of me getting a sample in this area. And the way we can get those probabilities is just by dividing each of these percentages by 100. So let's do that. Let's start with 2.5. 2.5 divided by 100 is 0.025, which means when I actually select my sample of 64 people and collect data from them, I have a 0.025 probability of getting a sample from the lower tail down here. In other words, I have a 0.025 probability of getting a sample mean that's more than 0.78 below the population mean, way out here. Now let's divide 95 by 100 to get the probability of the middle area. 95 divided by 100 is 0.95. So I have a 0.95 probability of getting a sample from the middle 95% area. I have a 0.95 probability of getting one of these samples that are within 0.78 of the unknown population mean. Now let's divide this by 100 to find the probability of me getting a sample from the upper tail. .5 divided by 100, 0.025 again. So the probability of me getting one of these samples out here in the upper 2.5% is a 0.025 probability. So let's recap what we just figured out. We figured out that we have these three areas. We figured out that this area down here is more than 0.78 below the population mean. We found out that this area is within 0.78 of the population mean. And we found out that this area is more than 0.78 above the population mean. We found out that 2.5% of the samples are in here, 95% of the samples are in here, and 2.5% of the samples are in here. And we also found out that when I randomly select my sample, I have a 0.025 probability of getting a sample from the lower tail, a 0.95 probability of getting a sample from the middle, and a 0.025 probability of getting a sample from the upper tail. There's one more thing that I wanted to mention. I wanted us to think about what would hypothetically happen if I didn't just select one sample of 64 people, but I kept on repeating my study over and over again. In other words, I take 64 people, I calculate the mean of the sample. I take another 64 people, I calculate the mean of the sample. I take another 64 people and calculate the mean of the sample. And I keep repeating my study over and over again with the same sample size. And each time I do it, I record the sample mean. Well, what's going to happen over time is that 2.5% of my samples will end up coming from here. 95% of my samples will end up coming from here. And 2.5% of my samples will end up coming from here. That's what I would observe over time if I kept on sampling over and over again. But in actual research, a person doesn't actually select samples over and over again hundreds of times. So what I just mentioned to you is actually something that would just, it's something that would happen in theory, but it's not something that a person would actually do in a real study. In a real study, a person would just take one sample and just reach a conclusion based on their one sample. Okay. So now we understand the 95% margin of error. We understand that it's the distance from the population mean to the lower end and the upper end of the middle 95% of the possible samples. Now I wanted to go through an example of calculating a margin of error with a different percentage. Maybe let's try to calculate the 80% margin of error. Well, if you wanted to do that, we would just have to switch our confidence coefficient. Instead of using the 95% coefficient like we did here, we would use the 80% coefficient. So let's go back to our table. If I want the 80% margin of error, I need to use 1.28 as my confidence coefficient. So it's going to be 1.28 times, well, this part right here won't change because the population standard deviation, it still is what it is, and I'm still planning to take a sample of 64 people, so those two numbers will stay the same. The only thing that's changing is my confidence coefficient. Now I know that this whole thing right here will come out to 0.4 because I already did the math. I already know that the square root of 64 is 8, and I already know that 3.2 divided by 8 is 0.4. So I could just skip ahead to step 3 and just multiply 1.28 by 0.4. I'm just skipping over a couple of steps. Oh, I'm sorry, this is actually the square root of 64. Because remember, it's the square root of my sample size, which is 64. So this whole piece right here is supposed to be the same thing that we had up here. So this whole piece right here that we see right here, this whole thing becomes 0.4. So if you multiply 1.28 by 0.4, we get 0.51 rounded. And that's our 80% margin of error. Now if I wanted to go through all of the steps with you again, what I would have done is I would have taken the square root of 64 and it would have become 8, like it did here. And then I would have divided 3.2 by 8, and then that would have become 0.4. But I skipped over those steps just because I already did them with you up here. So our 80% margin of error is 0.51. And I'm going to explain to you what this means. I need to draw a different curve. You might have noticed how I drew this shape as a normal curve right here. The reason why we know that the sampling distribution is normal is because I'm using a sample size above 30. The sample size is 64. So if the sample size is 30 or larger, then the sampling distribution is always at least roughly normal, regardless of what shape the population has. So once again, here we have the unknown population mean, the mean number of siblings of the entire JFK population, which is what I'm trying to estimate. Remember, this Greek symbol, mu, is just the symbol for population mean. So this is the unknown population mean that I'm estimating. So we have to imagine a boundary point down here again, and a boundary point up here. And the distance from the population mean to this boundary is our margin of error, which this time is 0.51. And 0.51 in this direction too. And this time it's the 80% margin of error. Since it's the 80% margin of error, that means that 80% of the possible samples have a sample mean between these two boundary points. Back when we calculated the 95% margin of error, we found out that 95% of the possible samples were between the two boundary points. Because by definition, the 95% margin of error is the distance from the population mean to the lower end and the upper end of the middle 95%. But the 80% margin of error is the distance from the population mean to the lower end and the upper end of the middle 80%. That's why I'm saying that 80% of the possible samples have a sample mean between these two boundaries. We have this boundary that's 0.51 below the population mean, and this boundary that's 0.51 above the population mean. And we've just discovered that 80% of the possible samples fall between those two boundary points. And if 80% of the possible samples are in here, that must mean that 20% of the possible samples are outside of this area, because 80 plus 20 is 100, and half of that 20% is down here, and half of that 20% is up here. So we're going to have to divide 20 by 2 to find out what these two tails are. Just like how we divided 5 by 2 up here and got 2.5, here we're going to divide 20 by 2 to get these two tails. So 20 divided by 2 is 10. So 10% of the possible samples are in this area, and 10% of the possible samples are in this area. So it looks like when I take my sample of 64 people, 10% of the possible samples that I could get have a sample mean more than 0.51 below the population mean. 10% of the possible samples have a sample mean more than 0.51 above the population mean. And 80% of the possible samples have a sample mean within 0.51 of the population mean. So up here, when we did this work, we found out that 2.5% of the possible samples have a sample mean more than 0.78 below the population mean. 2.5% of the possible samples have a sample mean that's more than 0.78 above the population mean, and 95% of the possible samples have a sample mean within 0.78 of the population mean. What we found out here by doing this work is that 10% of the possible samples have a sample mean more than 0.51 below the population mean down here. 10% of the possible samples have a sample mean more than 0.51 above the population mean out here, and 80% of the possible samples have a sample mean in here within 0.51 of the population mean. Now we could keep calculating other margin of errors if we want to. We could calculate the 70% or the 60%, but I think these are the only two that I want to do, because really the 95% margin of error is all that's calculated in actual studies. I just wanted to demonstrate calculating it with a different percentage, just to show you how it's possible to calculate it with a percentage other than the usual 95. So now I'm actually going to show you how the 95% margin of error is typically used in a study to reach a conclusion. And before I do that, I'm going to have to clear off a little bit of space from here. So now I'm going to show you how to create something called a 95% confidence interval. So what you have to do to create a 95% confidence interval is take the sample mean, the mean of the researcher's sample that was actually selected, and add and subtract the margin of error. So it's sample mean plus or minus margin of error. So I told you that the symbol mu is population mean. The symbol sigma right here is population standard deviation. X bar is sample mean. And n is sample size. And this symbol is the confidence coefficient. So this whole piece right here that comes after the plus or minus sign is the margin of error. And this x bar is the sample mean. So this is really just saying, take the sample mean and add and subtract the margin of error. And before I get into this, I wanted to also explain that this whole piece right here in red is the margin of error. But there's also a name for just this fraction right here, just the sigma over square root of n. This part right here, the sigma over square root of n, is called the standard error. The standard error is just what comes after this multiplication sign. So this fraction is the standard error. The entire red circle is the margin of error. So basically the standard error is inside of the margin of error. So now let's go on to talk about the 95% confidence interval. So now we have to imagine that I've actually done my study. I've actually selected my sample of 64 JFK students. I've recorded their numbers of siblings, and I've actually calculated the mean of my sample. Now let's imagine that the sample mean came out to 7.3 siblings. That was the average or the mean of my sample. What I do now is I take my sample mean and I add and subtract the 95% margin of error, which we've already calculated, and it came out to 0.78. We already know that this whole thing right here comes out to 0.78. So basically a 95% confidence interval is what you get when you take the sample mean and add and subtract the 95% margin of error. So we have to add and subtract separately. We'll add first, and then we'll subtract second. So 7.3 plus 0.78 would come out to 8.08. And I'm not sure what this is, so I'll use a calculator. 7.3 minus 0.78 is 6.52. So it looks like our 95% confidence interval goes from 6.52 up to 8.08. By adding and subtracting, we just found the lower end and the upper end of our confidence interval. The 95% confidence interval is a range of numbers. It's everything between this lower number and this upper number. And in a research study, this confidence interval is actually my final estimate of what I think the population mean is. So in this study, my final conclusion would be that I think the population mean is somewhere between 6.52 and 8.08. When a person is using a sample mean to estimate a population mean, their final conclusion is that they think that the population mean is somewhere inside of the confidence interval that they've created. And when a researcher has created a 95% confidence interval, what they actually say is that I'm 95% confident that the population mean is somewhere inside of the confidence interval. So I would actually say that I'm 95% confident that the mean number of siblings of the population is somewhere between 6.52 and 8.08. Now, I'm not completely sure that the population mean is between these two numbers, but I'm at least 95% confident that the population mean is in here somewhere. And I want to explain to you where this idea of 95% confidence comes from. Or I want to explain to you why I would actually say that I'm 95% confident. First, we need to discuss the situation in which the population mean actually will fall inside of the confidence interval. This is my confidence interval right here. It's my sample mean is at the center, and we added it and subtracted the margin of error. Which was 0.78. So this is my sample mean of, it was 7.3. This is the lower end, which is 6.52. This is the upper end, which was 8.08. This is the margin of error, and this is the other margin of error. This is the 95% margin of error. This is the 95% margin of error again. And this whole thing is called the 95% confidence interval with my sample mean at the center. Now, if it turns out that my sample came from the middle 95%, and my sample mean is within 0.78 of the population mean in this area right here, then in that case, my confidence interval does include the population mean. In that case, the confidence interval does cross over the population mean. Because if my sample came from this middle 95%, that means that my sample mean is close enough to the population mean for the population mean to fall inside of the confidence interval. Now, if my sample mean happened to be really low, or if it turns out that my sample mean is so far below the population mean that it's in this lower tail down here, then the confidence interval won't include the population mean. So if my sample mean is more than 0.78 below the population mean, In other words, if my sample mean is down here below this lower boundary, then the my confidence interval won't reach the population mean. Well, we already know that the upper end of my confidence interval came out to 8.08. So that's the upper end of my interval. The lower end of 6 came out to 6.52. So if my sample mean is down here in the lower tail, then that means that the population mean is somewhere above 8.08. The population mean is somewhere above the upper end of my confidence interval, and my confidence interval failed to capture the population mean. This is a situation that I hope didn't happen. I'm hoping that this isn't true, because I want my confidence interval to include the population mean. Now, if my sample mean is so high that it's up here in this upper tail, then my entire confidence interval falls above the population mean, and the population mean is somewhere below the lower end of my confidence interval. So if my sample mean is way up here in the upper tail, in the upper 2.5%, then that means that the population mean is somewhere below the lower end of my confidence interval. It's somewhere down here. So basically, if the sample mean is in the lower 2.5%, then the entire interval falls below the population mean. If the sample mean is in the upper tail, in the upper 2.5%, the entire confidence interval falls above the population mean. But if the sample mean is in the middle 95% somewhere, then the confidence interval does capture the population mean, because that's when the sample mean will be close enough to the population mean for the confidence interval to go across the population mean. And we mentioned earlier that there's a point when I randomly select my sample from the population, there's a 0.95 probability that my sample will come from the middle 95%. So that means that there's a 0.95 probability that I'm going to end up with a sample that leads to a success in capturing the population mean. There's a 0.95 probability that I'll get a sample somewhere from this middle area, and that my interval will capture the population mean. There's a 0.025 probability that my sample will come from the lower tail, and my entire interval will end up being too low. There's also a 0.025 probability that my sample will come from the upper tail, and that the entire interval will be too high. But I can at least take comfort in the fact that I know that I had a 0.95 chance of having a success and actually capturing the population mean like I want to. So there's basically a 0.95 probability of getting a sample. There's a 0.95 probability of getting a sample with a sample mean that's close enough to the population mean for the interval to end up actually capturing the population mean. One other point that I wanted to mention is that if I decided to repeat my study over and over again and take more and more samples of the same sample size over and over again, and I calculate a confidence interval around each sample mean that I end up getting, what's going to end up happening is 95% of my samples over time will come from this middle area in here, And that means that over time, 95% of the confidence intervals that I create will end up capturing the population mean. Only 2.5% of the confidence intervals that I create will end up down here, too low, and only 2.5% of the confidence intervals that I create will end up here, too high. So 95% of the time, my sample will come from the middle area, and my confidence interval will work. 2.5% of the time, my sample mean will come from this area, and the interval will be too low. And 2.5% of the time, my sample will come from here, and my interval will be too high. That's if I repeat my study over and over again. Now, like I said, I'm probably not going to repeat my study over and over again. I'm probably just going to do it once. So I'm probably just going to select one sample and create one confidence interval. And I have to basically hope that my sample comes from this middle area, and that my interval ends up being a success. Um, and one other point I wanted to make is that when you repeat the study with another sample, the entire confidence interval will end up changing. The reason why is because when you repeat the study with a new sample, you get a different sample mean. For example, if I repeated my study with a different sample, my new sample mean might be 8.5, which would mean that in my second study, I'd be adding and subtracting from my new sample mean of 8.5. So instead of creating an interval around 7.3, I'd be creating an interval around my new sample mean of 8.5, which would mean that the entire confidence interval would change. So just like how the sample mean changes from one study to the next, the confidence interval will change from one study to the next. But the good news is that when you repeat the study over and over again with different samples, and you keep creating more and more confidence intervals, 95% of the confidence intervals that are created over time will end up including the population mean. Only 5% of the confidence intervals that are created over time will end up failing to capture the population mean. So let's actually see what this confidence interval would come out to. This is 9.28. This is, I think, 8.72. So with my new sample, the confidence interval goes from 8.72 to 9.28. So in my second study, I would say I'm 95% confident that the sample mean, I'm 95% confident that the population mean is between these two numbers. So once again, I said, if you repeat a study over and over again, 2.5% of the time, the sample mean comes from here, and the entire interval is too low. 2.5% of the time, the sample mean comes from here, the entire interval is too high. 95% of the time, the sample mean comes from the middle area, and the interval does cross over the population mean. And since since the confidence interval does work 95% of the time, each time I create an interval, I can say I'm 95% confident that the interval did actually capture the population mean. One last thing I wanted to end with is I wanted to talk about what makes the margin of error smaller and larger. One thing that makes the margin of error smaller is having a smaller population standard deviation. So if sigma, the population standard deviation, goes down, if it's a smaller number, then the margin of error will be a smaller number. When sigma goes down, the margin of error shrinks. The margin of error also gets smaller when the sample size increases. So let's imagine that instead of taking a sample of 64 people, I took a sample of 100 people. If I did that, this margin of error would shrink down to a smaller number. For example, it might become 0.45 or 0.35. And actually, the larger I raise my sample size, the smaller this margin of error will become, because this middle area will keep shrinking. These two boundary points will end up moving closer. This boundary will move closer and closer to the population mean. This boundary will move in closer and closer to the population mean. And this margin of error will shrink. And one other point I wanted to make is that when the margin of error shrinks, when it goes down to a smaller number, the confidence interval becomes narrower, because the confidence interval is created by adding and subtracting the margin of error. So if the margin of error shrinks, then you're adding and subtracting by a smaller number, which means that the interval around the sample mean will become narrower. Because look down here. If the margin of error shrinks, then this bar becomes smaller, and this bar becomes smaller, and the entire interval is narrower. So the margin of error gets smaller with a smaller population standard deviation, smaller sigma, or a bigger sample size. And when the margin of error goes down, the confidence interval becomes narrower. Those are the last 2 points I wanted to make. And now I'll actually go to that website and show you what I want you to do. Before I do that, one thing you might be wondering is, what would you do if you didn't know what the population standard deviation is? Because you actually have to have data from all population members to get this population standard deviation. Well, it turns out that in actual studies, this population standard deviation is actually unknown. What you actually do in a real study is you have to actually substitute this population standard deviation with the standard deviation calculated from your sample. And it just substitutes and takes its place right here. And when a researcher does that substitution, there's actually another adjustment that has to be done with the formula. And we won't get into that adjustment in this video, or we might not get into it at all. But I just want you to be aware of the fact that in an actual study, when the population standard deviation is unknown, the researcher just substitutes it with the standard deviation from his or her sample data. And then when he or she actually does that, then the margin of error is actually called an estimated margin of error. It's not actually the true margin of error, it's just an estimate. So now let's get to the website. So here's the website that I wanted you to use. These are supposed to be the values from all the people in the population. Well, this is just supposed to be a made-up population. I guess 5 people, and these are all of their values. This actually lets you enter in your own numbers, so you can make up your own population. So here I'll just enter in some of my own numbers. So here I have a population of 6 people, and down here it lets me choose a sample size. Maybe I'll choose 4. This says samples to take 1. This means it'll take 1 sample at a time. And then I want it to calculate the 95% margin of error, which means I have to enter in 1.96. Remember, that was the value from the table. And then if I click take sample from the box, it's going to take a sample of 4 people. It's going to record their 4 numbers, and it's going to calculate the mean of the sample by adding the 4 numbers and dividing by 4. And the sample mean will be this dark box right here. Then it's going to calculate the margin of error by multiplying the 1.96 by the standard deviation of your population over the square root of your sample size, like we did earlier. So it calculated the margin of error for you, and it subtracted the margin of error and added it. So it's subtracted the 95% margin of error down here and added the 95% margin of error going up here. And this whole green line is the 95% confidence interval with the sample mean at the center. And then this blue line is the actual population mean. It's the mean of your entire population in here. So if you added all 6 of these numbers and divided by 6, you would get this population mean of 4. This black box is the mean of the 4 selected people from the box. Now you can repeat it by taking a different sample. It's going to randomly select a different group of 4 people and calculate the mean of that sample. This time the sample mean was a little bit lower. But notice how the sample mean is still at the center of the interval. And now we can do it again. So this time, these 2 sample means, or these 3 sample means, all came out above the population mean. This one came out below the population mean. But all confidence intervals so far have captured the population mean. So this is sample 1, sample 2, sample 3, sample 4. All 4 samples have had a confidence interval that crossed over the population mean. And if you keep going, you can repeat the study again and again with different samples. And eventually you'll get a confidence interval that doesn't include the population mean, because the sample mean will either be too far up here or too far away down here. And I'm going to have you make up your own population. Maybe you can include 10 numbers inside of here. And then I want you to, after you do that, after you enter in your 10 numbers, I want you to change this to 1.96. And then pick a sample size. And then do this 100 times. And see how many of them cross over the population mean. And then what I want you to do next is pick a different sample size, a bigger sample size, and do it 100 more times. And then
Once again, count how many of them cross over out of 100, but also I want you to pay attention to whether the intervals become narrower when you switch to a bigger sample size.